So our experiment is investigating resistive forces. I'm Andrew Brooks.
I'm Morgan Fellows.
And I'm Avi Pasula.
So our introduction is the main goal of this experiment was to find the relationship of light falling objects through a fluid, which was air, and the resistive force from that fluid. Also, our group wanted to see if changing the mass of the object would determine how fast the object would move as well as the resistive force acting upon it. In our results, we concluded that the higher the mass of the object, the lower the magnitude of the resistive force, which was a drag force, and it'll determine what that will be. In our experimental design, we basically used three different objects: a coffee filter, a styrofoam ball, and a paper plate, and they were all dropped from the same height, which was 1 meter. And each of these objects had a different mass. So our coffee filter had a mass of 1.8 grams, our styrofoam ball had a mass of 15 grams, and our paper plate had a mass of 19 grams. The fluid that was used, as stated before, was for all three objects was air, and the mass was the only variable that was altered during the experiment. Everything else was a control variable. This is a 1D experiment as the objects were only moving in the y direction.
So in this, our system schema would involve the object that is being dropped, the air, and the earth, and there's a gravitational force between the object and the earth and a contact force between the object and the air. And then for our force diagram, you would have the force of gravity acting downwards upon the object, and then you would have the force due to air resistance acting upwards on the object.
So using our tracker, we found these position time graphs for each of the objects that we dropped. And we basically just put them into Excel and then did a trend line for each of them. So using these trend lines, we were able to calculate the accelerations for each. So since the coffee filter and bowl both had a trend line that was linear, we could assume that the velocity versus time graphs were constant. And due to these graphs being constant, we can assume that both of the objects were at terminal velocity, so this gives us an acceleration of 0. For the paper plate, the equation for the trend line wasn't linear, so we basically just took the equation and we derived it twice, and that gave us an acceleration of that. After finding the accelerations, we just plugged the values into the FNet equation, which was FNet is equal to force of gravity plus force of drag and force of viscosity. However, we assume that force of viscosity is negligible because we were dropping things through air. So that leaves us with just force net is equal to force gravity plus force drag. And then after plugging in all those values, these were the forces that we got, with paper plate having the least amount of force and coffee filter having the most amount of force. So this showed that drag force was inversely proportional to the mass of the object.
So for our scientific reasoning for this is that there's a force due to gravity. The force will be acting downwards on the object, and this force would be different for each of the objects because the objects had different masses. There is also a force applied due to air resistance. This force is acting upwards, and in this particular experiment, it is called the drag force. Our limitations for this experiment were that we used Tracker, and the Tracker software wasn't accurate in terms of velocity, so we were forced to calculate the velocities and the accelerations. And also during the process of recording our videos for the tracker, there might have been some human error.
In conclusion, so we basically, according to our data and our conclusions and our calculations, we can reasonably conclude that the heavier an object, the less drag force that object will experience. This conclusion was formed using the position versus time graphs as well as the accelerations that we calculated using the graphs.